Alright, welcome back. This is the video for Monday, Tuesday of this week. This is the video that's going to introduce you to Newton's very first law. So, take just a quick second to enjoy this Yoda gif that I put on the first slide because we're talking about forces. We have to talk about Yoda and the force. May the force be with you. Okay, whatever. So, let's go into a hypothetical scenario first before we jump into Newton's first law. Let's say that we decide to get a cup of coffee, and we're going to fill it to the brim, like you see in the picture there, and then we're going to start walking around a track. Alright? Now, you're not going to just spill the coffee in any random order. There's going to be specific points as you're walking around that track that you're going to most likely spill the coffee. Where do you think those points are going to be? Interesting to think about. There's 3 specific points that you are most likely going to spill your coffee. The very first point is at the very beginning when you were originally stopped and you had your cup of coffee and then you started going again. Okay? That is going to be the first point where you probably spill the coffee. The second point is when you have started moving, you're going good, and you're like, woo, I'm not going to spill anything, and then you go and you change directions. Meaning you go around that first curve of the track. You're most likely going to spill your coffee at that point. The third part where you are most likely going to spill your coffee is towards the finish line. You're walking, your coffee is still kind of okay, you're good, and then all of a sudden you stop. That's the third part where you're most likely going to spill your coffee. Now, why is it that those are the 3 points where you're most likely going to have an accident? That is because of Newton's first law. Newton's first law has 2 parts. It says that an object at rest is going to stay at rest unless it is acted upon by an unbalanced force. The second part of Newton's first law says that an object in motion will continue in motion at the same speed in the same direction, again, unless acted upon by an unbalanced force. So let's come back to that coffee scenario and see how Newton's law relates to it. In that very first part, when I said, okay, if you are at the starting line, you are currently stopped, meaning you're at rest, and then you start going in motion. You're going to most likely spill your coffee then because an object is going to stay at rest unless it's an unbalanced force, and at that point, the unbalanced force causes motion, which is causing your coffee to go whoop right out your cup. The second scenario, the second part where you're most likely going to spill your coffee, is when you're in motion, but then you change your direction, right? So at this point, we're dealing with the second part of Newton's first law, where you're in motion and you're like, I just want to go the same speed. I want to go the same direction. I don't want to change anything at all. But then you have to turn, and as soon as you turn, unbalanced force, you're going to cause some sloshing in your cup, and you're going to spill your coffee. Same idea with the very last one. Again, you're in motion. You want to stay in the exact same motion that you've been going, the same speed, the same direction, but because you have to stop, that's an unbalanced force, causes some sloshing in your cup, and you're going to spill your coffee. So, you can go ahead and test this idea at home, at your own house, in your no making messes at my house or my classroom. But test it. It's interesting to see, how long or how far can you go carrying a very full cup of water before you spill it. And it's all because of Newton's first law. So, we're going to take this knowledge with us as we go back through and review system schema and how objects interact and the forces that result because of their interactions. Very quickly, I want to review the forces that we learned because it's going to be a few days since you guys did this stuff. So the first force that we learned about was the applied force. That is a push or pull that is applied by a person or another object. This is a contact force, which means there has to be touching between 2 objects. So if I'm holding onto something and I pull it, or if I'm touching something and then I push it, that's an applied force. The next force is the force of gravity, or you might hear it as the gravitational force. This is a non-contact force, or what we could call an action at a distance force. We don't have to necessarily be touching to experience the force of gravity, right? Like if I have my sticky notes and I let go, they fall down towards my desk because of the force of gravity. Again, I can't really touch gravity, but it exists and I can feel its effects. The next force is the normal force. My hint to you is that whenever you see the force of gravity, there's most likely going to be the normal force, as long as there's two objects that are touching. So if I'm looking at my coffee cup right now, gravity is acting on that coffee cup because it's drawing it down towards the table. But why doesn't it just go straight through the table? There's a normal force. The normal force is supporting my cup to help it counteract the force of gravity. The next force is air resistance. This one is pretty self-explanatory. You have to be in the air or interacting with air molecules to experience air resistance. Very small objects have what we call negligible air resistance, which means it's so small we almost don't even know that it's there. But very, very large objects like airplanes or skydivers, I almost call them bungee jumpers. I'm like, that's not it. Skydivers with their huge parachutes, right? Those objects will experience air resistance, and they have to account for it when they're doing their thing. Air resistance is a contact force. I don't know if I mentioned that already. It's a contact force because even though we don't necessarily see the air, there are air molecules in air that we are coming into contact with, and that's what's causing us to slow down. The next one is the spring force. The word spring is in that name, and so it alludes to the fact that a spring force is within a spring. Whenever you have a spring, you can compress it, meaning you can squeeze it and get the coils closer and closer together. That causes a spring force. You can also stretch a spring, and that also causes a spring force. Now, the amount that you compress it or stretch it is equal to the amount of force. So if you do it a little bit, it's a little force. If you do it a lot, it can be a big force. The spring force, what's interesting is that the force works in both directions. So it's not just a one-directional thing, like if I push something or pull something, a spring acts so that the arrows are going both ways. Same idea. This type of force also acts on both ends. This is called the tension force. This is a force that is seen through materials like cables or wires or ropes, or if you're walking your dog and you have your dog's leash in your hand, that is a tension force. You can feel it being pulled tight, and I think the word is taut, right? You can see it go taut. That's tension force. Again, acts equally on both ends, so we use double-sided arrows to represent them. Okay, now we're going to go back in time a little bit, and we're going to do some more practice with system schema. Remember, system schema are ways that we can represent how objects are interacting with each other so that we can really figure out what are the forces that are present and what's causing motion or not causing motion. In the following slides, we're going to be looking at what forces are present and then drawing the system schema, but we're not actually going to be drawing, it's more like drag and drop and label type of stuff. I want to point something out before I move on from here. In this video, I'm only going to be going over questions number 1 and 2. So as you're watching this, you can be filling out your own questions 1 and 2. You can just copy the answers that I kind of give you. But then you will be responsible for doing questions 3, 4, and 5 on your own. So how do you figure out which problems are where? Notice on this slide you see the number 1 in the left-hand corner. That means that this is problem number 1. So again, I'm going to be doing all of the slides dealing with 1 and 2. You will have to do slides 3, 4, and 5. Not slides. Questions 3, 4, and 5 on your own. Okay, so here we are. Scenario number 1. It says a block hangs at rest from the ceiling by a piece of rope. So the scenario looks something kind of like this. What forces might be present in this scenario? Well, considering that the block is going to be drawn downwards, there is definitely going to be gravity, so I'll say yes there. There's no springs in this scenario, so I'll say no. Because there's a rope that's attached between the brick and the ceiling, that's going to cause tension force. Is there normal force? No, because it's not resting on anything, really. Is there friction? No, because again, the brick's not really touching anything, like sitting on a table or rolling across the floor or sliding across the road. There's none of that, so no friction. And because there's no person or object pushing or pulling on it, then there's no applied force. So when you see a table like this, all you have to put is yes or no for which forces you think is there. All right, now we go to the next part where we are going to create the system schema for this scenario. Remember, in system schema, the circle that has the dotted circle around it, that's the object of focus. So in this one, we were looking specifically at the block. So I'm just going to click and drag that box. Then we have a few other things that we need to fill out. What's helpful is knowing the difference between a dotted line and a solid line in your system schema. A dotted line means a non-contact force, which really the only non-contact force we deal with a ton is the force of gravity. So this line here would be the force of gravity. Now, who is the one object that's responsible for creating gravity? That would be Earth. So I'm going to put Earth there. Then we have to kind of think through the rest of this. The block is attached to what, which is attached to what? So the block is attached to a rope, which is attached to the ceiling. Now, what are the forces in between those? Between the block and the rope, there is tension force. And remember, the force of tension acts in both directions. So between the block and the rope, there's tension, and between the rope and the ceiling, there's tension. All right, let's go on to number 2. A block hangs from the ceiling by a spring. So is there gravity? Yes, because there legit is a spring there. There's a spring force. Is there tension? No, because there's no rope, wire, cable, leash, things like that. Is there a normal force? No, because it's not resting on anything. Is there any friction? No. Is there an applied force? No. So just gravity and spring force. Now let's take a look at the system schema. Again, the circled dot is the object of focus, which is the block. The dotted line is typically always your force of gravity, and the thing that's responsible for creating gravity is the Earth. In the similar way to number 1, we were looking at the block is connected to what, who's connected to what, and that spring is that connecting factor. The block and the ceiling, the spring is the connecting thing. So again, just like tension forces, spring forces work in both directions. So there's the spring force between the block and the spring, and a spring force between the spring and the ceiling. Okay, so like I said, these answers, you need to make sure that you copy them down into your own slides, and then once you have that done, you need to go through questions 3, 4, and 5. So that's going to be a ball is shot into the air with a cannon. 2 skydivers are falling at terminal velocity, which means they are in free fall. And a block rests on top of a table. Your job is to go through those scenarios, answer the force table questions, and also do the system schema. That's where you end for asynchronous time. Okay? If you have any questions, let me know. I am here to help you.